Hi, I'm Vivek Arte, and I'm going to talk about dual mode non-interactive zero knowledge and property transfer. This is joint work with Mihir Bellare. We start by recalling non-interactive proof systems, which were first constructed by Blum, Feldman, and Micali in 1988 in the Common Reference String model. In the Common Reference String model, there are two parties called the prover and the verifier, and there's assumed to be a trusted setup algorithm that generates a common reference string and sends it to both parties. A relation is a function that takes as input the common reference string, a statement X, a witness W, and returns either true or false. We are interested in NP relations, which is when the function R is polynomial time and the size of the witness is polynomially bounded in the size of the statement and the size of the common reference string. The language associated with this relation and the common reference string is defined as the set of all statements that have a witness satisfying the relation. As part of the proof system, the prover is supposed to have a statement X and a witness W such that the relation on the CRS X and W is true. The goal of the prover then is to convince the verifier that the statement X is in the language. In order to do this, the prover runs the proof generation algorithm and sends the generated proof to the verifier along with the statement X the proof corresponds to. The verifier then runs the verification algorithm and uses it to decide whether the proof is valid or not. That is, if the verification algorithm outputs true, the verifier is convinced that the proof is valid, otherwise not. We require proof systems to be complete. That is, proofs that are generated by the proof generation algorithm for a statement in the language must always lead to the verification algorithm returning true for the same statement and proof. Beyond completeness, there are other properties of proof systems that are often aimed for in the literature. The soundness property requires it to be hard for a polynomial time adversary to construct a proof for a statement that is not in the language, such that the verification algorithm accepts the statement proof pair. There are different variants of soundness existing in the literature. We will in particular look in closer detail at two notions that we will call SNDE and SNDP. The extractability property is also known as the proof of knowledge property. It requires that if the prover is able to produce a valid proof for a statement, then there is an extractor algorithm that can obtain the witness from the information the adversary has access to. The extractor is given access to a trapdoor that underlies the common reference string. The witness indistinguishability property guarantees that if there are two witnesses for a statement, it is hard for an adversary to be able to tell which witness was used in order to generate the proof. Finally, the zero knowledge property guarantees that a proof generated for a statement in the language reveals no information about the witness for that statement. The concept of dual mode proof systems was first introduced in the 2006 work of Groth, Oskrovsky, and Sahai. In this technique, there are two proof systems, pi0 and pi1. The two CRS generation algorithms generate common reference strings which are computationally indistinguishable from each other. Both proof systems have proof generation and verification algorithms which are identical to their counterparts in the other proof system. So what is the benefit of such a pair of proof systems? Groth, Ostrowski, and Sahai use the perfect soundness of one mode and the computational indistinguishability of the common reference strings in order to prove computational soundness of the other mode. This computational soundness, coupled with the perfect zero knowledge of this other mode, led to the construction of the first perfect zero knowledge argument system, a major open question of the time. We now look at some of the other papers that consider dual mode proof systems and look at the requirements they place on the individual modes. A common thread in all these works is that each mode has some specific requirement to be met. For example, one of soundness or extractability in one mode, and one of zero knowledge or witness indistinguishability in the other. For example, the work of Albrecht et al., in which dual mode systems are used to build multilinear maps, has a perfect soundness and extractability requirement in mode 0, and a perfect zero knowledge and witness indistinguishability requirement in mode 1. The Groth-Ostrowski-Sahai paper we saw earlier has perfect soundness requirement for mode 0 and a perfect zero knowledge requirement for mode 1. The work of Bellare et al. Is used for constructing anonymous credentials. It requires perfect soundness in mode 0 and perfect witness indistinguishability in mode 1. We now introduce the terminology of transference. We have a pair of proof systems, pi0 and pi1, that are dual mode proof systems. That is, the CRS generation algorithms generate common reference strings that are computationally indistinguishable. If one proof system, say pi0, satisfies a property p, then we can use that along with the computational indistinguishability of the common reference strings to claim that the other proof system, that is pi1, satisfies the computational analog of property p. We say that the property p transfers if this claim holds. The purpose and applications of prior work depend on the transference of different properties between the modes of the proof systems. Therefore, we ask the question, which properties transfer? We are interested in studying transference for a number of different properties like zero knowledge, witness indistinguishability, extractability, and soundness. We now take a look at our contributions. We define dual mode proof systems so as to only have the CRS indistinguishability requirement and no additional requirements on the individual modes. We call this requirement mode indistinguishability. We formulate the question of transference and ask which properties transfer. We prove some negative results. We show via an explicit counterexample that the SNDP notion of soundness does not transfer between the two modes of a dual mode proof system. We also show, again via an explicit counterexample, a separation between the SNDE and SNDP notions of soundness. This result holds for regular proof systems. Both our counterexamples are based on the hardness of the decisional Diffie-Hellman assumption. We then turn to positive results. We provide an abstraction of property specifications and then state and prove a transfer theorem. This allows us to capture all the positive results simultaneously with a single proof. As a result, we are able to show that the standard definitions of zero knowledge, witness indistinguishability, and extractability do transfer. Let's now look at the syntax and definition of dual mode proof systems. The syntax of dual mode proof systems is very similar to those of regular proof systems. Just as in the regular case, there are three algorithms corresponding to CRS generation, proof generation, and verification. The CRS generation algorithm syntax is different for dual mode proof systems. In this case, it takes an additional bit as input, mu, which is used to denote the mode of the induced proof system. The dual mode CRS generation algorithm thus induces two non-interactive proof systems depending on the choice of the bit mu. We emphasize that these induced proof systems are just regular non-interactive proof systems and can satisfy properties just as normal. The only requirement we make of our dual mode proof systems is that the common reference strings generated in these two modes be computationally indistinguishable. We call this property mode indistinguishability, and it is the only property that we will mandate for our dual mode proof systems. We now move on to transference. As we have seen, transference refers to the scenario where we can conclude the satisfaction of the computational analog of a property P in one mode based on the satisfaction of the property P in the other mode and the mode indistinguishability of the dual mode proof system. Some examples of properties of interest are soundness, zero knowledge, witness indistinguishability, and extractability. We will see that a property P transfers if it can be specified in polynomial time. We turn now to negative results. We first stop to take a look at the property of soundness, which is defined with respect to a relation R. At a high level, for soundness to hold, the adversary must not be able to return a statement proof pair such that the statement is not in the language, but the verification algorithm returns true. There are two variants of soundness depending on whether the definition is penalizing or exclusionary. This distinction between penalty style and exclusion style definitions was first considered in 2015 by Bellare, Hofheinz, and Kiltz in the context of public key encryption and key encapsulation mechanisms. These two definitions differ in the kinds of queries the adversary is allowed to make. The penalty style definition, which we denote by SNDP, makes no restrictions on the polynomial time adversary. Instead, it includes in its win condition a check of the language membership for the statement in the query, which is highlighted in blue. This prevents the adversary from winning using a query with a statement in the language. Note that the membership test will not be efficient for languages in NP, which are the languages of interest to us. In the exclusion style definitions, which we denote by SNDE, the adversary is restricted to almost never make queries in which the statement is not in the language. We formalize this by requiring the adversary to belong to a class of membership-conscious adversaries. A membership-conscious adversary is one which picks a statement belonging to the language with negligible probability. In the described game, this corresponds to the adversary setting the bad variable to true with negligible probability, as is highlighted in green. The win condition for an adversary in this case, as a result, is simply a check for whether the verification algorithm accepts the proof as valid. We now turn to the question of which of these definitions are good for applications. We notice that the penalty style definition is more application enabling and useful for applications, while the exclusion style definition is less so. We consider as a canonical application the use of non-interactive zero knowledge to construct digital signatures, as was first done by Bellare and Goldwasser in 1990. We see that the SNDP style definitions allow us to construct digital signatures, while the proof doesn't go through in the case of the SNDE style definitions. We now describe how the two relations of soundness compare to each other. It is easy to see that the penalty style definition automatically implies the exclusion style definition. This is because an adversary that attacks the SNDE notion will also attack the SNDP notion with only a negligibly smaller probability. On the other hand, the reverse implication does not hold. That is, SNDE does not imply SNDP. We show this separation via a counterexample. More specifically, we construct a non-interactive proof system and a relation R, such that the proof system satisfies the exclusion definition of soundness, but at the same time, it does not satisfy the penalty definition of soundness. This counterexample is based on the assumption that there exists a group generator such that the decisional Diffie-Hellman problem is hard to solve in that group. This shows the SNDE definition is strictly weaker than the SNDP definition. We now show that for dual mode proof systems, the penalty style definition of soundness does not transfer. The intuition is that this property fails to transfer because transference requires a reduction adversary to test for membership in the language. As we have mentioned, languages of interest are in NP, which means that membership tests would be inefficient. We show that there exists a dual mode proof system dpi and a relation R such that dpi is mode indistinguishable and one induced mode of dpi is SNDP for the relation, but the other induced mode for dpi is not SNDP for the relation. We show this by means of an explicit counterexample that is again based on the hardness of the decisional Diffie-Hellman assumption. The dual mode CRS generation algorithm generates the common reference string in two different ways based on the value of mu. From this, it is easy to see that the mode indistinguishability follows directly from the DDL assumption in the group. Further, we define the relation in such a way that the language consists of all group elements except g raised to ab. The proof generation algorithm we construct is trivial, while the verification algorithm we construct verifies all statements X in the group and returns true for all these statements. As a result, in order to break soundness, the adversary needs only to pick x equals g raised to ab. We now look at the attack against SNDP when mu equals 0. Notice here that the CRS itself contains g raised to ab. Therefore, the adversary can simply return that value picked from the common reference string along with a trivial proof and then break soundness with probability 1. When mu equals 1, we show that we can reduce the SNDP property to the DDH assumption in the group. We turn now to positive results. First, we want to show that SNDE transfers. So here we are given that one mode of the dual mode proof system satisfies SNDE soundness, and we also know that the dual mode system satisfies mode indistinguishability. If it was the case that the other mode did not satisfy SNDE soundness, this could be used as a distinguishing test for mode indistinguishability. It's important to note that this depends on the polynomial time nature of the SNDE game. If that were not the case, a distinguishing test based on the SNDE game would not be polynomial time and therefore would not be able to be run by the distinguishing adversary. We would prefer not to have to prove individually for each property of interest whether that particular property transfers. Therefore, we create the abstraction of a property specification. A property specification captures the game that corresponds to a particular property P. We do note that there are slight differences to the property specification based on whether the game problem is of a decision type or a search type. The property specification absorbs all of the oracles of the properties game into its single oracle and maintains state in such a way that it can perfectly simulate the property game. As a result, we are able to construct property specifications that perfectly match the behavior of their target properties game. The transfer theorem states that a property specification that runs in polynomial time corresponds to a property that transfers. We see that the property specifications for zero knowledge, witness indistinguishability, extractability, and the exclusion form of soundness all have polynomial time property specifications. However, the property specification for SNDP is not polynomial time. This is because of the win condition. The membership test in there is not polynomial time for languages in NP. Thus far, we have discussed everything in the common reference string model. The designated verifier model is set up in such a way that only a specific verifier will be able to verify the proof. This is captured by having a secret verification key that is given only to the verifier. The designated prover model, meanwhile, is set up such that only a specific prover will be able to generate proofs. This is done by having a secret proving key that is given only to the prover. The preprocessing model has secret information handed to both the prover and the verifiers. This is captured by using both the proving and verification keys simultaneously. We note that all results discussed here work in these other models as well. So to summarize, we have defined dual mode proof systems with only the mode indistinguishability requirement. We also define what it means for a property to transfer, and we ask which properties transfer. We prove that SNDP, the penalty style definition of soundness, does not transfer via an explicit counterexample based on the hardness of the decisional Diffie-Hellman assumption. We prove via a general framework that many properties like zero knowledge, witness indistinguishability, extractability, and the exclusion form of soundness do transfer. We also show that the penalty style definition of soundness is a strictly stronger notion than the exclusion style definition of soundness. The main takeaways are that we must be careful while using dual mode systems and applications. We must check that we actually do get the properties we require from the induced proof systems and not expect it to be implicit due to transference.